All right. So let's get started. First, I'll say something for anyone watching this later. Um, I would recommend working or trying to work through some of the problems posted in the announcement and ahead of time, just so you can kind of practice them first before just seeing how they're done. Um, and also, I'm going to proceed in the order that I wrote them out. So if um, you want to try to jump to the middle to find some of the problems, I'm going to go in the order written uh, on the exam sheet, or not the exam sheet, but the problem sheet. And then also for the people here, um, if you feel like you need to leave, I mean, depending on how long we go, you won't hurt my feelings if you have to head out early. And then you can watch whatever you miss um, later after I get it posted to Canvas. Okay. I think before I actually get going in the problems, I want to lay out what is sort of a potential general strategy for series. And so this is basically a checklist of our different types of series, as well as what you're looking for when you're deciding if you want to use a certain test or not. And the order that you mentally go through might be different, but this is one way of doing it. So the first way is check to see if your series is just a P series or geometric. So these are really different looking series, but both of these types, there's a single number you look at, and you don't even have to do any calculations like take a limit or something, but there's a single number you look at, and that is the whole ball game. That tells you if it converges or diverges. So that can be a first thing to look at and know that right away you can knock those out without really going any further. Next up is the test for divergence. So here, this is taking the limit of the sequence and seeing if that's 0. And if it's not, you can say diverge right away. This is a test that won't always work, and in maybe many cases it won't, but it's often not too hard to check. Even if you don't write something out, you could kind of glance at this and say, yeah, it looks like the terms go to 0. I don't have to do this. Then what comes next are many of them at the same level. So it's not really, you have to check these in order, but the rest are for these different tests, what are we looking for? So for instance, if your series is close to a P series or a geometric series, do a comparison. And there are two types of comparisons. I, in general, always go with a limit comparison unless it seems like there's a pretty clear inequality that you could use. Next up, if it's alternating, then a kind of obvious choice is try the alternating series test. Next up, if there's a lot of multiplication around, and in particular, factorials, then use the ratio test. And I guess here's an example where, while this is written in order, some things kind of override other things. In particular, even if you have an alternating series, if there's a factorial, you probably want to go with the ratio test. And in general, if it's alternating but sort of complicated, you might not want to use the alternating series test. Next up, if there are not nth roots, but rather the other way, if there are nth powers, use the root test. And then lastly, if your sequence, if you look at the, or think of it as a function, and the integral of that function is doable, then maybe the integral test. There are also some other things that we've talked about. Some others, like maybe if the terms aren't positive, then maybe put absolute values on and check if it converges absolutely. That can be something. Maybe it's telescoping. But also, I think something to keep in mind is that the series I give you, we will have the tools to determine what happens. We just need to figure it out. So even if you aren't sure, say focusing on these, which tests to use, you can maybe start ruling some out, saying, well, it's not alternating, there aren't any nth powers, so probably not the root test, I don't know how to integrate it. You can start getting rid of some, and then what you're left with, maybe you have to try one and it doesn't work, but then just try something else. And then one last thing before we get into actually trying out these series that I mentioned, I'll say, if you actually need to find the sum, there are really only two ways that we can do that. It's going to be geometric or telescoping. So there just aren't very many series that we can actually find the sum of. So if you see a problem that says find the sum, or if it converges, find the sum, then that limits what tools you might end up using, because we can't find the sum in very many cases. Okay, so now let's get into some of these examples. So the first one was 2 to the n times n squared over n plus 2 factorial. Okay. And this first batch will be check if they converge or diverge. So in this case, we're trying to think what is the best test to use. And a giveaway is the factorial, unless, and I don't know if I can really think of it right now, but unless you have a good reason for not using the ratio test, probably use the ratio test. And so the ratio test says the limit of an plus 1 over an with absolute values. That doesn't do anything in this case since it's all positive, but often what this would do is it would get rid of any alternating part. So then an plus 1 is all of these n's we replace with n plus 1. So that's 2 to the n plus 1, n plus 1, that whole thing is squared, and then n plus 3 factorial. Since it's already n plus 2, we add 1 to that. And that whole thing is divided by just this term, 2 to the n squared over n plus 2 factorial. So then we simplify, and the way that we simplify and write what comes next is often really similar. We're going to flip this and multiply it. So that means this bottom factorial is going to be on the top of the fraction, and this top 2 to the n and n squared is going to be on the bottom of the fraction. Knowing that's how things get flipped, we can group things according to what type they are. So we get 2 to the n plus 1. Sorry, that looks kind of weird. 2 to the n plus 1 over 2 to the n. Then we have the powers, n plus 1 squared over n squared. And then the factorials, n plus 2 factorial over n plus 3 factorial. And then we get some simplifying. With the exponentials, we're left with, we have one more factor of 2 on the top, so that gives us just an extra factor of 2. Here we can multiply this out, n squared plus 2n plus 1 over n squared. And then with factorials, we actually write out the multiplication that happens. So starting with the number inside the factorial, that's n plus 2, n plus 1, and so on. And then on the bottom, we start with n plus 3. And then if we subtract 1 from that, this 3 goes down to a 2. And then we get n plus 1 next. And we keep getting the same factors we did above, but now there's this extra n plus 3. So tons of simplifying, all of those things cancel. And what we're left with is this 2 and this n plus 3, and I'll group those things together. And then n squared plus 2n plus 1 all over n squared. And the important thing, and why, and I did this in some examples in class, multiplying this n plus 1 squared out is not the most important thing, because what you can tell without actually multiplying out is whatever happens, I'm going to have an n squared and then smaller stuff. So the limit of this part, which we're still keeping here, this thing is going to converge to 1. And when you have polynomials around, that always happens with the ratio test. So this part goes to 1, and as n goes to infinity, n plus 3 goes infinite, so 2 over n plus 3 goes to 0. So we get 0 out. Then we need to remember for all of these tests, what do we actually look at? We get this number, what do we do with it? And for the ratio test, what we're looking at is this is less than 1. And when that's the case, the series converges, and we'll say by the ratio test. Questions about this one? Okay. So recap, the factorial is the big giveaway that it's going to be the ratio test. Whenever you do the ratio test, the powers, that's always going to end up with some limit that goes to 1. And so if that's all you have, you get 1 and the ratio test is inconclusive, but the other parts give us something which doesn't go to 1. Great. So let's look at this guy. Let's say n minus 1 over n cubed plus 1. So in this case, this is a rational function, and rational functions, or one way of describing them, is they look like p-series with extra stuff. And so what we can say is if we focus on these two biggest terms here, the biggest power in the top and the bottom, we can use those to find a p-series to compare this to. So we're going to compare this to n over n cubed, and canceling a factor of n, we get 1 over n squared. And this comparison series, we do need to say what it does. It's pretty quick since it will often be a p-series or geometric, and those are pretty quick convergence tests. So 1 over n squared, you can say this converges by the p-test because p is 2, and that's bigger than 1, and that's when we converge. Okay. So this is what we compare it to, and the comparison thing converges, but that's not enough. It's not just enough to say it looks like this. We really do need to check that this is a good comparison. And what that means is, or how I'll do this, is the limit comparison test. If you're going to do a direct comparison, it's harder when there's more stuff because then the inequalities have to be just right. I think you could do a direct comparison. The inequalities will work out the way you want them to. So this is less than 1 over n squared, but it's hard to see that. And rather than worrying about if it works out exactly the right way, the limit comparison test says in the limit, the small stuff is just going to go away, so we don't have to worry about it. So we take the limit as n of the original series, n minus 1 over n cubed plus 1, then divided by 1 over n squared, flip the fraction and multiply it into the top. We get n cubed minus n squared, and then n cubed plus 1. The powers match. They don't have any numbers in front, so it's a 1 in both places, and so this limit is 1. Then we want to say we got a 1. In some cases, that's not good. For the ratio and root test, 1 says we don't know. For the limit comparison, it is good because this means you got a finite number that isn't 0, And that means that these are actually a good comparison. So this, I'll say for emphasis, we didn't get 0. So the original series converges. And why we get to say converges is not the fact that this is a 1 here, really. Getting a number other than 0 says the series you started with will do the same thing as the comparison series. So it's not that we're saying, oh, I got a 1 as compared to a 1/2 that determines convergence. It's if you get a finite number, the two series, the one you started with and the one you picked to compare it to, those will do the same thing. And the comparison series is easy to determine what it does. Questions about this one? Then our next guy is -1 to the n times n squared minus 1 over n squared plus 1. So in here, there's the alternating part. The thing that might trigger is alternating series test. So how that starts is that we focus on Bn, n squared minus 1 over n squared plus 1, and we take a limit of this. So the limit of n squared minus 1 over n squared plus 1, the powers match, and they both have ones, unwritten ones in front of those biggest powers, so we get 1 here. And that's not actually what we wanted to see. For the alternating series test, you want it to be converging to 0 and also decreasing. But the biggest thing is often that the limit is 0. And so we don't get that. So what we can't actually say is that the series diverges by the alternating series test, but there's some other test that we have which does explain what happens. So if this limit is 1, and in particular not 0, if we put the alternating piece back on, then what happens is this limit actually doesn't exist, because the non-alternating part is going to 1, which means when your alternating part is positive, you're getting close to 1, but when your alternating part is negative, you're getting close to -1. And so half of it is going to 1, half is going to -1, and you can't converge and be going different places. If you converge, you're going to one place. So this doesn't exist. And so the reason why the original series diverges is actually by the test for divergence. Because if the sequence from the series, if that does anything other than go to 0, then we know the series diverges. So for alternating series, this is often the way that things will go. Take the limit of the non-alternating part. If it does go to 0, then also check that it's decreasing, and then you get to say converges by alternating series test. If it doesn't go to 0, then you actually get to back up and say, well, then the alternating version, that limit just doesn't exist, and then we can use the test for divergence. questions about this one? Okay. Then number 4. So this one is a little kind of strange looking, but we can try to look past the weirdness and think about what our tests are and which ones apply in which situations. So here we have the nth root of 2 minus 1, that whole thing all raised to the nth power. So this nth root of 2 is something which hasn't really showed up before. But the way to look at this and say, well, that's weird, I'll have to deal with that at some point. But the part to focus on, which helps us determine which test we want to do, is actually there's a big ol' nth root here, or nth power. And so if we use the root test, we'll get rid of that. And then we can see what's happening with this nth root of 2. So because there's a big nth power, we'll use the root test. So we're going to take the nth root of an. The absolute values don't do anything, so we're just going to take the nth root of the nth power, and then we get this cancellation, which is exactly why we picked the root test in the first place. The nth root of this nth power n goes to infinity. Those cancel each other out, and we get the nth root of 2 minus 1. Okay. To deal with this thing, there's a small fact which has appeared in maybe a few examples, but is still sort of a strange fact. And that's that if you take the nth root of any polynomial, and actually the 2 counts as a polynomial, usually they have variables in them, but a constant does count. This converges to 1 as n goes to infinity. So this fact is why if you only have polynomials around, the ratio or the root test doesn't work because the limit ends up being 1. But if you have other stuff, then sometimes it will work because that other stuff is just going to become 1 and you don't worry about it. In this case, what we look at is this nth root of 2, that's going to converge to 1. The 1 that's here doesn't do anything. And so this expression converges to 0. If you felt like playing around with a calculator, if you keep taking higher and higher roots of 2, so the square root, cube root, fourth root, and so on, you can actually check that it gets close to 1. So that limit is 1. 1 minus 1 is 0. Now we want to check, what does it mean if in the root test you get a 0? And the root test, like the ratio test, says 0 isn't that special. What we care about is that we got something less than 1. And since we got something less than 1, the series converges by the root test. Questions about this one? I think that the root test part of it is not so bad, but also there's this other kind of root thing happening. So then let's try this one. Let's take the sum of 1 times 3 times 5 times dot 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 2n minus 1 over 2 times 5 times 8 times so on, so on, so on, up to 3n minus 1. Okay. So what's happening here is that we have repeated multiplication. The sequence is on the top, we're going to multiply more and more odd numbers. So the top, so we'll write that out in a second. But on the bottom, it's not odd numbers, but we start at 2 and we keep jumping up by 3. So it's 2 and then 3 more is 5, 3 more than that is 8. The next one's 11 and then 14. So we keep going up by 3 each time. And that creates a list of numbers, and that's what we keep multiplying by. So the sequence looks like 1 over 2, then the first 2 odd numbers, and then the first 2 numbers by starting at 2 and jumping up by 3, then 3 odd numbers, and then we go 2 times 5 times 8. And then we have the first 4 odd numbers, and then we go up 2, 3 more is 5, 3 more is 8, 3 more is 11, and so on. So that's the sequence that we're making, and we're adding all of these up. Okay. So given something like this repeated multiplication, this is like, or this should make you think of a factorial, and it's almost that, where we have repeated multiplication, but it's not exactly a factorial, because factorials say start somewhere and have everything. So like 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And we have gaps in here. We're only doing selected numbers that we keep multiplying. So it's not exactly like a factorial, but it's repeated multiplication. And because of that repeated multiplication, the ratio test is essentially the only thing that's going to work. So if we want to find this an plus 1 over an, when we put an plus 1 in here, we get 1 times 3 times 5 up to 2n minus 1. That's the n term. If we add 1, what we think of is going to the next odd number here, which is 2n plus 1. Another way of writing that out is if you stick n plus 1 in for this n here, so we'll say this 2n plus 1 is 2 times n plus 1 minus 1. And if you multiply the 2 out and combine the numbers, you get to 2n plus 1. So that's where this comes from. And the same basic move is on the bottom. We have, starting at 2, we're going up by multiples of 3. We get to this 3n minus 1. But if we put an n plus 1 in here and simplify the expression, we get 3n plus 2. As a kind of check that happens is, we said we were going up by 3s. If you add another 3 to 3n minus 1, you get the negative 1 plus 3 gets us to plus 2. So this is the next multiple of 3 that we would get. then we get a n here, 1 times 3 times 5, 2n minus 1, and then 2 times 5 times 8, 3n minus 1. Okay. Questions about getting to here, because the next step is cancellation. But before we cancel stuff, I want to make sure that people are mostly okay with what we actually got. All right. So then what I'm going to do is a little, there's a lot of stuff to write, and I'm going to fall back on the fact that we've done a bunch of ratio test problems, and the simplification for factorials kind of all works the same way, in that if you flip this and multiply, what happens is everything cancels except these last two factors from the top and bottom. So what is left after you flip and multiply and cancel are these extra two factors, 2n plus 1 over 3n plus 2. And then you've done the canceling. This is what you take a limit of. And this is thankfully sort of nice. It's the powers match, it's just an n. So we take the fraction from the coefficients to get 2/3. And then we get to say that's less than 1. So this series converges by the ratio test. So I think the hardest part of this is this monstrous bunch of factors here. But the way we deal with it is by putting n plus 1 in for this n, that gives us, or that tells us what the extra factor is. And as a sanity check, these numbers keep going up by 2 when you go from an odd number to the next number. And from -1 to +1, that is a jump of 2. And the same thing on the bottom. You're going up by 3s, and from -1 to +2, that is a jump of 3. Okay. So the next one is one where it's not really clear what the best way to do this is. And in this case, what I say is some of these, like there's a factorial around, it's really clear you want to use the ratio test. In some cases, it won't be as clear, and that happens, and you need to sort of go through your options and think about what we can do. So in this case, if we think about what I guess what tests we can use, so it's not actually geometric. It's close to geometric, so we might think comparison, but it's a little weird, so we'll maybe wait on that. So maybe a comparison test. We're not going to try to integrate this. The ratio and root test don't work. The root test doesn't work because if you take the, or here I changed the variable, you take the kth root of this. The kth root of a sum, you can't break it apart into the kth root of the 3 and the 4. So the root test seems like it could work, but it doesn't quite work for us. And it's not alternating. I said we can't integrate it. So what we have left is a comparison test. That's really the thing that we are going to try to do. But I think what you might try is the limit comparison test. And I think that's hard to make actually work. So let me switch to red for trying something that doesn't quite seem like it'll work. What you might try is there's a 5 to the k and the 4 to the k. When you're comparing exponentials, those are the bigger base grows faster. So you might think, what if I compare this to 5 to the k over 4 to the k, which is geometric. That's 5/4 to the k. And that diverges since the r is 5/4, and that's greater than 1, or greater than or equal to 1. But if you actually try to do the comparison, at least I haven't written this out, but I don't think it works quite the way we want it to. If we try to find the limit of this, we get 5 to the k over 3 to the k plus 4 to the k divided by, I'll use this version that's broken up in a fraction, 5 to the k over 4 to the k, flip and multiply, and we get 5 to the k over 3k plus 4 to the k, and then 4 to the k over 5 to the k. And then we can cancel the 5s, which is good. But then we have 4 to the k and 3 to the k plus 4 to the k. And something we haven't actually done is talk about limits like this. If you try to use L'Hopital's rule, because this is infinity over infinity, the exponentials don't go away. You just get a bunch of natural logs out. So L'Hopital's rule doesn't work. You can make this work if you're a little sneakier about it. A sneaky way is try to factor a 4 to the k out of the bottom. And if we do that, then what happens if we take out a 4 to the k? Well, there isn't one of those here, so we have to divide by it. And that becomes 3/4 to the k. And then 4 to the k is the entire thing here, so we get +1. To verify this, if you multiply 4 to the k back through, you get just 3 to the k first, and then 4 to the k second. These things cancel, and we get 1 over 3/4 to the k plus 1. And this is actually the limit we can't take. So I guess when I said the limit comparison test doesn't seem like it works, it's not that it can't work. It's just that we have to make some kind of surprising moves. But if we make those moves, then this geometric sequence on the bottom, that converges to 0. And we get 1, which, since we're doing a limit comparison test, says that the original series diverges by the limit comparison test. So it turned out this is a good comparison, but this move is maybe not something you'd think of. So let me do this another way, which I think is something that is less sort of out of left field, but still a little surprising. 5 to the k over 3 to the k plus 4 to the k. So another thing which won't work is if you try to do a direct comparison with 5 to the k and 4 to the k. So what we can say is 3 to the k plus 4 to the k, well, that's bigger than 4 to the k because you have the extra thing. If you flip these, so taking the reciprocals changes the direction of the inequality. So this is less than 1 over 4 to the k. And then if you multiply on top by 5 to the k, we get that our series is smaller than 5 to the k over 4 to the k. And this isn't the direction that we want, because this series, we said this on the other page, the series with these terms diverges, but being smaller than something that diverges isn't helpful. There's room for you to still diverge, or you could be small enough to converge. So that way doesn't work either. But here's a move which is a little variation of this, which does actually work. What we can say is that, so here's in black something which is going to work. 3 to the k is less than 4 to the k because you have a smaller number, so it's not as big. Add 4 to the k to both of these. So 3 to the k plus 4 to the k is less than or equal to 4 to the k plus 4 to the k. And that is 2 times 4 to the k. Now focus on these two parts of the inequality. And here, this is like what, or close to what we had before, but the inequality is going in the other direction, which is actually what we wanted. We had some comparison here, but the inequality was flipped the wrong way. If we try these same moves, so now with these two parts, flip the inequality, 1 over 3 to the k plus 4 to the k is bigger than 1 over 2 times 4 to the k. and then put that 5 to the k on the top. 5 to the k over 3 to the k plus 4 to the k is bigger than 5 to the k over 2 times 4 to the k, which, rewriting a little bit, is still a standard geometric series, but we have this a rather than just a 1 there. So we are able to get an inequality for this comparison. And so we get to say that the series 1/2 5/4 to the k diverges because r is 5/4, that's bigger than 1. So the original series diverges by direct comparison. Okay. Questions about this problem, either version of it, the limit one or this direct one. Okay, so I'd say about this one, it is a little, it is kind of unexpected how we end up doing these. But the moves that we're making are not something we've never seen before. But we maybe haven't had, or we haven't really had examples putting them together in this way. But sometimes you need to be a little bit creative. A demonstration of the power of these tests is that if you can combine them in sort of different ways, you can actually get a lot of different series that you can determine the convergence of, not just somewhere it's pretty clear that what test to use and it works without really any hiccups. So the last two problems I want to do are of this different type, which is the absolute convergence, conditional convergence, or divergence. And so this one is negative, the first one is -1 to the n over the square root of the natural log of n. Okay. So in this case, a way that you can start is the alternating series test. It is alternating after all, and the non-alternating part, the Bn, is not so complicated, n times the square root of the natural log of n. In that case, the alternating series test is not too hard to apply. So in this case, this Bn, one thing you can say it is decreasing. And the common way that this happens is since the bottom part is increasing. N and the square root and the natural log, those are all things that are going up as you put in bigger and bigger numbers. And so if you combine them, that still keeps happening. And then we also need to check that the limit as n goes to infinity of this, n squared natural log of n, is 0. Because not only is it increasing, but it's going infinite, and 1 over that then must be going to 0. So that means this series converges by the alternating series test. Which in this case is not everything, because that means we can rule out just straight diverging, but then we need to know what happens if you take off the alternating part. Does it still converge, or does it not anymore, in which case we have this middle conditional convergence. So let's put that on its own. To check for absolute convergence, we're looking at this series 1 over n square root of natural log of n. So now we need to think, what tools which of our techniques or tests for convergence can apply? And a bunch of them get ruled out. We know this goes to 0. It's not alternating. The ratio and root tests don't work well with this sort of thing. There aren't like powers and multiplication, so this isn't really good for that. If you try a comparison test, you might think, what if we compare it to 1 over n? That ends up not working. You get 0 or infinity depending on which one you write in the top of the fraction, and that says that you can't use the limit comparison test. Also, the issue is that the bottom is bigger than n, so this fraction is smaller than 1 over n, so that means we can't use the direct comparison test either. And then we've like ruled out everything that we possibly can, except for one thing. The test that will actually work here is actually the integral test. And the integral test, I don't really like it that much. I would rather not do an improper integral. But one place where it does show up is, well, I guess one place is if nothing else seems like it's going to work. But also, when you have natural logs, the integral test is often something that can help. And if you're thinking the integral test, you should check, do I think I can integrate this? If I change the n's to x's, could I integrate that? And in this case, you can, because we have the natural log, its derivative is 1 over x, and we have that 1 over x right there. So this is set up for a u substitution. So let's do that. If you're going to use the integral test, it starts by saying, think about the function 1 over x square root of the natural log of x. And this is positive, continuous, and decreasing on, we need to pick an interval where it's all of these things. So it's actually always decreasing because the bottom is always increasing. Continuous, you have to miss 0, you have to miss 1 because the natural log of 1 is 0, and that makes the bottom 0. But 2 is okay. And so from 2 to infinity, we've missed all the asymptotes, and so we're good. And it's not so important that that 2 is the smallest number that works, but there has to be some point past which you miss all the asymptotes and you're positive and you're decreasing. So then we get to set up the improper integral. For that, because it's a little complicated, or I mean, not as complicated as some of our integrals, but it's not the sort of thing we can just do in line as we're doing our improper integral. So we'll do this integral first. As I hinted at, the way to do this is u is the natural log, and du, its derivative is 1 over x dx. And especially if we separate this into the square root of the natural log, and then the x we can write as a separate fraction multiplied 1 over x dx. So now substitute everything in. We're integrating the square root of u du. For integration purposes, let's write that with a negative exponent, and then use the power rule. So increase negative 1/2 to positive 1/2, divide by that new exponent, dividing by 1/2 gives us 2. So this is 2 times the square root of u, which is 2 square root natural log of x plus c, which if you don't write it, it doesn't matter because we're going to immediately jump into an improper integral. So from 2 to infinity, we integrate this. Putting a bunch of steps together, we're taking a limit as t goes to infinity. We are integrating this, which means we get this antiderivative, 2 squared to the natural log of x. And that's what we're evaluating from 2 up to t. Then substitute in 2 square root natural log of t minus 2 square root natural log of 2. And then as t goes to infinity, the natural log of t is going into infinity. The square root of something going to infinity is infinity. And 2 times something going to infinity is infinity. And this constant we're subtracting doesn't stop it. So this limit is infinity. So then we get to wrap this up. The whole point was we were looking at this series, and the integral test said, since the integral diverges, the corresponding series diverges also by the integral test. And then actually, going all the way back, we originally said, here's this series, what does it do? And we figured out that using the alternating series test, it converges, so it converges normally, but if we lose the alternating part, it doesn't converge anymore. So the actual last thing we get to say about this is I'll put in a great connecting word, hence. It's a few pages back, so we'll actually write this series out. -1 to the n over n squared of the natural log of n conditionally converges, because it does converge, but not if you remove the alternating part. Questions about this part? And it's spread out over a couple of pages, so I'm happy to go back to any other part of it.
This isn't really for this question, but in general, for the integral test, what would it take for it to converge and not diverge? Like,
so what would happen would be if in this limit, usually it's if you end up with a fraction here, then the fractional part will often go to 0 and you're just left with this number. So I think if we made some kind of variation, if this square root was 1 over x natural log of x squared, if that was the thing we're integrating, this square root becomes a square, and you would get 1 over, what is it? You get like -1 over the natural log of x would be the antiderivative. And so then if you set up the integral, you would get to this limit. You take the limit as t goes to infinity, -1 over the natural log of t plus, what would it be? 1 over the natural log of 2. And then in this case, the natural log of t going infinite means this is 0, and then you're left with a number.
Okay, thank you. So it'll be like that if it's not going to infinity.
Yeah, the way the improper integrals will work is there's some part with the variable. Usually that will go infinite or it'll go to 0. There could be some other things, but those are the most common things.
Okay, so it only diverges if it goes to infinity and it converges otherwise.
I guess what could happen? If for some reason this limit just didn't exist, that would also mean diverges. But it's if this limit gives you any finite number at all, then it converts. Then we would say the integral converges. That was the terminology we used. And if the integral converges, then the series also converges.
Okay, thank you.
All right, so then let's wrap this up with one last one. So the same setup. So this is absolute convergence, conditional convergence, or divergence. And we'll look at -1 over n to the n. One way of looking at this is that this is actually an alternating series. If you raise the top and bottom separately to the nth power, rather than writing it as a fraction, you get -1 to the n over n to the n. And you can use the alternating series test here. The Bn is 1 over n to the n. This is positive, or sorry, this is decreasing and it's going to 0, so we can use the alternating series test. The reason why I'm not actually going to go that way is, as originally written, there's this big ol' nth power, and that says use the root test. And the ratio and root test both give you absolute convergence if you're below 1, or divergence if you're bigger than 1. So one way you can try to do it is, if you think the ratio or root test can go, use that test, and you might not even need that the 2 steps of alternating series, then the other one, just jump right into it with the root test in this case. So if we try the root test, so this is the square root of the nth root, the absolute value of -1 over n to the n. The absolute values has the effect of killing off the alternating part. So it is useful to recognize there's this alternating part and that's going to go away. So we still have the nth root of 1 over n to the nth roots cancel, or nth root and nth power cancel. So we have the 1 on the top and the n on the bottom. That's 0, less than 1. So then we get that the series converges absolutely by the root test. So a lot of times the alternating series test is a way to go, but if you think you can use the ratio and root test, or root test, that can be faster if it ends up working. Okay. Any last questions? So that's the last of the problems. And I can go back and talk about any of the other ones that I did.
This isn't a question for any of the problems, but for the exam tomorrow, I know earlier, whenever we were first learning series and sequences, we kind of like had to make our own series of sequences. Is the exam just going to be about convergence and divergence?
So there could be a question that looks something like, here's a series. So this is kind of going to cheaply use the last example that I saw that we did. But here would be an example for this sequence, and let's say -1, 1 over 4, -1 over 27, 1 over, I don't know what the number is, but 4 to the 4th, ... There could be something like, find the general term an, then maybe determine if an converges or diverges, either one. So in this case, what happens is you're given the list of numbers and you want to think, what is the pattern here? So an is, so it's doing this alternating part, 1, -1, and that means we know there's some kind of alternating part. Then on the bottom, especially by the time I get here, I kind of maybe give it away a little bit, but this is on the bottom here, that's 1 to the first power, that's 2 squared, that's 3 cubed, and then 4 to the 4. So that says that we really are getting n to the n, where n is the first term, second term, third term, fourth term, and so on. And that means, so that's the general term, then go in and say, what does this series do? And then you go into the problem we just did. So a lot of it will be kind of the way we've been doing. You're given the general term, figure out what to do. But this is another way that it could be phrased. Given the list of numbers, identify the pattern that gives you the series, and then use the convergence test on that series once you figure out how to write it.
Okay. Is there anything else that's not on the like the practice page that you think we need to worry about?
Um, I don't think so. Yeah, I think what the tests we didn't really talk about, we didn't do a telescoping example. Um, but I think we got all of the other tests. Um, yeah, so it'll, right, there might be a little bit of sequence stuff, but it'll mostly be these tests for convergence. All right, then I think we'll wrap up there. Hopefully this has been helpful. But other than that, I'll see you tomorrow.